Have you ever wondered why regression is called regression? What is it that's regressing where? So let's look at this example. This is just a simple linear regression where we want to predict the height of a son based on the height of the father. And we would say this looks like a fairly good model. It seems we're getting a fairly good prediction out of this. But what we're doing here, are we really predicting the height of the son solely based on the height of the father? If that were the case, then we would rather have a model that looks like this. So in comparison to the one that we had before, this is a model that doesn't have an intercept term. This is a slope-only model. So we say the son's height should be a certain factor times the height of the father. So could be, we try to predict by saying the height of the son is the height of the father, or the height of the son is 1.1 times the height of the father, but essentially we're only changing the slope, but we have no intercept. Now you can see there seems to be something off about this model, and if we have a bit of a closer look, then we see that for those heights, those lower heights of the father, these values always seem to be above what the model predicts, or the prediction of the model is too low. And on the other hand side, the very tall fathers, we also see to some extent that generally the values lie below what the model is predicting. So what these values here are doing is they are regressing towards the mean. The mean is shown here as this green line, and this is why this is called a regression model, because these values are closer to the mean than what a model without considering the mean would predict. And this is actually exactly the case that Francis Gaulton was looking at, predicting the heights of sons based on the heights of fathers, when he came up with this term of regression model, because he observed we need this intercept term. We get a better prediction if we include the population mean of the value that we're trying to observe. If we're now looking at it, just removing the model, then we see, okay, if we were only using the intercept, then this also doesn't look like a great model. So we see there should be something like this slope. We want to include our predictor as well. And this is typically the way how we're looking at our models. So we are mainly interested in the prediction of our response variable based on the explanatory variable. So this is what gets our focus, and we're generally forgetting, however, that most of the predicting is done by looking at the population mean. So maybe next time we look at a model, we should not say the response variable is predicted by the explanatory variable mainly, but this intercept, the population mean of or the sample mean of our response variable, actually plays a big role. This is not a problem in practice. So in practice, when we do a comparison, we would generally compare to the now model. So our p-value of our predicted slope, or p-value for including a predictor, generally is against the now models, the model that has the intercept. Or if we do something like calculating an r-squared value, then it's the variance explained by the model. So it would be the variance around the mean. So in practice, that's not a big deal, but we can consider next time we generate a model that actually most of the explaining, or in many cases at least most of the explaining, is done by the population mean rather than by these predictors that we put in, because values like regressing to the mean.